There's still so much that we don't know in this field, and that's almost what's so exciting about it. It's a really exciting time to be a cancer immunologist because these therapies, these CAR T-cell therapies, have gone from being injected into the first patient 5 years ago to being FDA approved last week at this time of filming. So to take this living drug in 5 years to essentially go from the bench to the bedside is really quite extraordinary. And so because of this rapid translation, which has been driven by a high clinical need for these therapies, but because they have been translated into patients so quickly, there's still a lot about the basic cell biology that we still don't really understand. So we understand a lot about programming a T-cell through its T-cell receptor, but when we change that to this synthetically engineered receptor, we still don't really understand how that affects memory, whether these T-cells can persist, whether they can be recalled, much like they would in a vaccination type approach. So if the cancer gets cleared and if the cancer comes back, is there a pool of memory cells that will rapidly respond in a secondary T-cell response way? How can we minimise off-target effects? How do we minimise pro-inflammatory cytokine secretion and inducing these cytokine release syndromes in patients? And also, how can these T cells overcome the very immunosuppressive environment, sometimes in solid tumours, which essentially switches them off? And I think the answer to those will be in the future of combination therapy, that these therapies won't be used in isolation, they'll be used in combination. So there's still so much we don't know, and I think that's what makes it a really exciting time to, I guess, really uncover new knowledge and contribute to, new knowledge to the planet. We have these small breakthroughs and small findings and results that come hot off the press, every week, every few weeks, certainly every couple of months. And so, it's really exciting. I mean, right now we're, again, hot off the press, but we've just think we've discovered a biomarker for serial killing, which means being able to identify which T cells are serial killers versus ones that aren't. That's pretty cool because we could ultimately use that to understand T cells that are inside tumours. Are they doing their job? Are they able to kill? And we might be able to actually measure that. So that's pretty exciting. And I think we're now moving into this new era of personalised medicine, where we can take tumours out of patients, identify what's novel or different about that tumour and compared to a healthy tissue, say for example in the brain, and design new CARs against them. I mean, so it's a really, and which will ultimately hopefully go back into the patient in the form of a clinical trial. So yeah, it's a really exciting time. I think we're just really lucky to be working on the cutting edge on something that's so exciting, and ultimately reminding ourselves every day why we do what we do, and it's ultimately for the benefit of patients and their families. Right now, my lab is moving into new territory in the form of studying brain cancer. Brain cancer kills more children than any other disease. Fact. Including congenital heart defects, including leukemia, brain cancer kills more children than any other disease, and hundreds of children around the world every year die of brain cancer. The 5-year survival rates are about 5%, so it is, for 95% of children, it is a death sentence to receive a diagnosis of brain cancer. So obviously this is probably the hardest challenge any family could face. There have been no new treatments in decades. They're resistant to chemotherapy. Quite often it's only surgery or radiation, that are the options that treating physicians have. So that means we need new approaches. We need to be thinking more cleverly, thinking creatively outside the box. And I think that's where the form of a living drug, like a T-cell drug, like a CAR T-cell, may be a really great place to start. So we're looking at designing CAR T-cell killers and applying them into the brain with the view that we want to create a super serial killer, so a T-cell that's going to kill lots of tumour cells, not kill any healthy brain cells, without the side effects of edema and swelling in the brain.